So good morning. My talk today is going to be on using ICESat-2 for shallow water bathymetry. If you're not familiar with bathymetry, we're talking about water depths, and with ICESat-2 particularly, we're talking about water depths in the range of 0 to 40 meters. This is kind of important because ICESat-2 provides a global capability for bathymetry, and it's one of the only satellites that provides direct measurements of the seafloor. So typically how you can do satellite-derived bathymetry is by looking at changes in reflectance from imagery, and then referencing that to some other on-the-ground survey, either from shipborne or airborne methods. But ICESat-2 is kind of really the first of its kind to be providing these direct measurements of the seafloor at a global scale. So it's got a lot of people really excited, and that's part of the reason that they're developing a new bathymetric product for ICESat-2 as well. So what we'll be going over today is, in lieu of that bathymetric product, most people doing bathymetry tend to work with ATL03. And not everyone who's an oceanographer or hydrographer wants to get that in the weeds on ATL03, as I'm sure some of you today have already figured out. So what I'm going to try and do today is to get anyone interested working in bathymetry from, very little ATL03 background, just the stuff that we've talked about in the Hackweek so far, to being able to get refraction corrected depths that you can compare to some other external data source, whether that be airborne or shipborne LiDAR or some other survey method. Particularly, we'll be looking at methods of photon analysis for single tracks. So we won't be doing some of the great work that Karina and Zach showed where you're plotting multiple tracks over an area of interest. We're just going to be looking at one ICESat-2 track. We're going to be looking at methods of analyzing that photon data that maybe aren't the highest fidelity, but are the easiest to understand and get the ball rolling on your own research if you're interested in doing bathymetry. Additionally, there's going to be a little bit of work here on interactive visualization to kind of maybe hype up Philip's upcoming tutorial on data visualization as well. So feel free to poach any of that code. A lot of the code in this notebook isn't actually specific to bathymetry. There's really only a couple cells that you need that are specific to bathymetry. So I hope that it's useful for maybe folks who aren't looking just at seafloors as well. So to start, I think everyone here so far has an Earth data account, has some basic familiarity with slide rule based on the previous data access tutorials, and has some familiarity with the photon data from ATL03. Has anyone here not set up Earth data or slide rule and isn't comfortable with that? Okay, that's fine. The other thing that we'll be looking at today is, so let's just start here. If anyone's following along, you can access this tutorial via the Hackweek website, GitHub. So it's under like book, tutorials, and then bathymetry, and that's where we are. So we'll go ahead and just get started by importing some packages that we need for this tutorial and initializing slide rule just to save us a little bit of time later. So you can follow along here if you'd like. If you don't feel like following along or digging in, I provided a couple of cookie cutter examples that you can switch between. But one of the best ways to get started looking at ICESat-2 bathymetry is to start with this website, OpenAltimetry. If you're not familiar with OpenAltimetry, it provides this great interactive way to quickly kind of inspect ICESat-2 ground tracks, how much signal they have, what the potential signal looks like. So we'll start here and we'll pick maybe some example data over the Florida Keys because they have a lot of really great clear water and bright sandy seafloor. So what I'm trying to do here is I'm trying to identify a good track with bathymetry for the purposes of a single track analysis. So we can see the ICESat-2 ground tracks here. And if we click one, it'll show us the track ID, which we'll want to make a note of for later if we like the data from this track, and it will show us the date. These pre-populated dots over the ground track, these correspond to ATL08 signal. There's not a bathymetric specific signal that shows up on OpenAltimetry, but usually you can use ATL08 as a pretty good proxy for whether there's water surface or ground data nearby. You'll also notice that sometimes there's a gap. So right here on this track, there's a gap about here. Sometimes this is just due to a cloud, but more often when you're looking at bathymetry on OpenAltimetry, ATL08 has a 10-kilometer buffer from the coastlines. So for example, if I go to the Great Barrier Reef, where you have a lot of great shallow water bathymetry from ICESat-2, even if you have great signal, if you're too far off the coast, you won't see that here. So, this is a great example here. So this track clearly has great signal. It's probably a clear day, but it cuts off. So if you're looking for bathymetry and OpenAltimetry, this is just something to note, that it doesn't necessarily mean that you won't have data there. So if we're looking to inspect these photons specifically, we can select the region using the select a region tool here. And I'm actually doing this on the fly, which is probably not a great idea. I didn't like pre-scan this track, so let's hope this actually has something. So open altimetry will show us the photon data pretty clearly. So this might be kind of disappointing if you're looking right off the bat. You say, okay, well, this is the Great Barrier Reef. We'd expect a little something more than this. And I'm showing this for a reason, right? So ATLO3 signal confidence is not optimized for bathymetry. There's a couple different surface types, land, ocean surfaces, and they're great for those applications. But for bathymetry, there's maybe some other things you might want to be aware of, particularly that bathymetric returns are often a much lower density than the ocean surface or land surface returns that you might expect elsewhere. And even if you have a really strong ocean surface return, the bathymetric photons are often a very, very small percentage of the overall photons in a scene. So you'll notice here that open altimetry is showing a 7.69% data sample rate. That's just to ease the load on their servers. But a lot of the time, you may have to view all data to see bathymetric photons in ICESat-2 data. So we'll say view all data here. And it might take a second. And it's maybe not immediately obvious, but we do see the returns are much denser. And if we were to zoom in, I bet we'll get some great clarity. The other thing to note about ATLO3 signal confidence, like I said, is that it's not optimized for bathymetry. So you may want to show low confidence photons, or particularly photons included in the buffer. So I'm going to reset the zoom just so you can see a little bit better. So if you're only using ATLO3 signal confidences to try and find bathymetry, you're probably going to miss a lot of bathymetry. So this is just something to note. And if you're using open altimetry, as I do pretty frequently, it's just something to be aware of. So if you are following along and you want to try and break my notebook on the fly and tell me about it in about 20 minutes, you can make a note of the date here. So in this case, this track is 2022, August 19th. And right here, it shows the track ID. So this is the same thing as the reference ground track. So this is going to be 901. If you found your own example, that's great. Save that. And then we'll go to, let's see here, we'll go back to the notebook. Oh, sorry, I switched browsers here. Move the Zoom window. Great. So we'll go back to the notebook. If you saved an RGT here, so let's see, what did I say that one was? Track 901. We can specify that. And the date 2022, August 19th. And like I said, if you don't feel like following along this much in detail, there's a couple pre-provided examples. So for example, you can select a bounding box over New Zealand, Japan, North Carolina, the Bahamas. We'll try out this user defined one, and hopefully this won't break everything. So what this is doing is this is basically just saving that, and this includes kind of the switching for the predefined areas. So we're setting up our query for slide rule. We are using slide rule to download the photon data in this instance because it's maybe not the best optimized for single track analysis, but if you're looking at a large area of interest, it's a really great place to start. So I wanted to provide some of the infrastructure there. There's a lot of code in this cell. Don't worry about it. This is not an IPy leaflet tutorial. This is a bathymetry tutorial. But what I'm doing here is I'm just setting up a map and saving off a bounding box as you select it. So I believe we were looking at open altimetry somewhere over the Great Barrier Reef. Oh God, I didn't save which one it was. So you can select a bounding box manually there for your area of interest. I'm going to go back and switch to Japan, a pre-selected example here. So you can modify the bounding box using polygons here to the left, or you can trash them. It's similar infrastructure for a lot of different use cases. We can verify that the bounding box that we've drawn is what we would expect, and just kind of see the target RGT that we saved as well. As many of you probably know at this point, there's 6 ICESat-2 beams. Whether GT1R or GT1L is the strong beam can depend on the orientation of the satellite, and that's kind of tricky to manage. And I'm sure other people, if you're interested in looking into that in more detail, can explain that to you. That we're not going to do that on this one. So for this track, we're just going to take the center of the beams, and we're going to take the strong beam from that pair. So in this next cell, we're starting to set up our query for slide rule. So a couple things to note. We're trying to return all photons here regardless of signal confidence. So I noted earlier that ATL03 signal confidence may not be optimized for bathymetry. So when we're querying the data, we want to make sure that we're pulling just all the photons that we can analyze a little later. The other thing I'm noting in this slide rule query is we're providing a YAPC parameter selection to calculate a density-based measure of photon signal. That's going to be very helpful for us later as well. And then I think this is probably the first time so far this week that we've shown this is extra parameters from ATL03. So if you've taken a look at ATL03 in detail, there's actually a whole lot of photon rate data, things like latitude and longitude, but also things like geoid heights, pointing parameters of the satellite. So for here, we're pulling in reference azimuth and reference elevation. That tells us from the satellite's position in space, at what angle is the laser actually hitting the surface. So you can see a little bit behind the scenes here, but I've already ran this notebook cell to avoid any problems with everyone running notebook cells at once. So feel free to run it on your own and see how long it takes. For me, it took about a minute. There's some other things here that kind of make things a little easier for this demo purposes, but I'd point you to the other data access tutorials if some of the notes in this cell look a little bit confusing. So in the next cell, we inspect the columns that slide rule has provided back to us. Primarily, we just want to note that we're getting the reference azimuth and reference elevation and the geoidal heights back from ATL03. We'll use that geoid helps us kind of flatten out the water surface in the photon data, and the reference azimuth and elevation are kind of the key for bathymetry with ATL03 because it allows us to correct for the laser refraction through the water. If you've ever stuck your straw in a glass of water and noticed that the light bends a little differently, you have to correct for that when you're looking at heights from ICESat-2. In the next cell, we use kind of a reduced data frame function provided from the slide rule Grand Mesa demo to subset the data that we're returning from slide rule. I think in this case, we're only really looking at 1 day track and 1 ground track. So it's there for use for you later. The other thing that we're doing here is we're computing an along track meters measure. So just how far from the start of this track are the photon data proceeding. And then we're also computing an orthometric height using the onboard geoid from ATL03. In this case, I believe ICESat uses EGM08 geoidal heights, and slide rule very nicely resamples those at the photon rate for you as well. And then this is just a little fun cell of me playing around with IPy leaflet. But if you run this, it should go back to this map up here and plot the ground track for you. So you can actually get a much closer look of where the data that we're going to be looking at is, and we can reference this later as well. So we can see that there's a lot of great coral reefs over here in Okinawa, Japan, but there's also some terrain, some buildings, and there's probably some clouds as well in your area of interest or some of the other examples in this notebook. But yes, this is just a great method of visualizing the data, I think. I just wanted to pause and see if there were any questions so far about any of the data access before we get into the photon analysis. Great. And then just this last cell really quick is we're going to specify the limits for plotting. Oftentimes you might get some noise either just from the surface signal dropping out, and then you have background photons. So it's easier to just kind of upfront specify, hey, how deep are we actually looking for bathymetry, right? So in some cases, you may be looking for very, very shallow bathymetry. If you're in the Seychelles and you have a coral reef like half a meter underneath the water, you might want to use different processing measures than if you're looking at the Great Barrier Reef and you have some seafloor, 40 meters underneath the water, which is not impossible. It is somewhat uncommon to get ICESat-2 that deep, but it's definitely out there. So here we'll start looking at what the photon data actually looks like for bathymetry and how we might use some of the onboard signal measures to subset the photon data in a way that's meaningful for our analysis. So this cell, you can take a look yourself, but it sets up 3 plots. So in the top plot, it plots the ATL03 signal confidence flags provided by slide rule for the land surface confidence. There's an ocean surface confidence, but generally land is the best you're going to get for bathymetry for various reasons, even though it's not perfect. If you're curious which one of those is best, that's the one I would recommend. This also will plot the YAPC photon scores, which I find to be more helpful for this type of work. And it will also plot a thing called the quality photon flag. This example doesn't show it. You may see it in your own research, but I didn't want to get too in the weeds. But if there's a very, very bright surface, sometimes ICESat-2 can present false returns or false surfaces approximately 2 and 4 meters beneath the surface of the actual ocean, the actual water surface. This is just due to various things in the instrument and the data processing pipeline. And I'm definitely going to push that off to maybe people who are more informed and more capable of talking about that. But if you're looking for bathymetry and you're just looking at the photon data, you would want to remove those because those aren't actually returns underneath the water. It's not actual seafloor, but in the photon data, it's going to look like photons underneath the water. So for this track, we can see that the ATL03 signal confidence is actually doing fairly well. It's picking up a lot of the bathymetry that we would expect. And you can see that some of the subsurface noise is also picked up in the high confidence measure, although some subsurface noise is successfully removed. We do see that YAPC tends to do a little bit better. So there's a couple different approaches in the literature. This is not like the be-all end-all approach to bathymetry. Some people use custom signal finding using density-based measures. YAPC is nice because it's fairly similar, and because it's built into slide rule, it saves you a lot of work coding. So we'll use that here, and we can see that a lot of our bathymetry is actually, probably in this example, if we were to set a threshold of maybe 100, the 100 value of YAPC, that would probably do pretty well at removing most of the subsurface noise. So we can actually specify that here. I was using 25 before just to ensure that we look at all the photon data, but we can set that manually if we'd like. So the next cell will isolate basically any of the photons with a YAPC score higher than the threshold that we set. And then in this cell, what we're doing is, you may have noticed in this track, and maybe the track that you found as well, there's water, but there's also a whole lot of land. In a lot of these cases, ICESat-2, the way that the ground track intersects the coastline, can be hard to predict. And sometimes for bathymetric analysis, the easiest first thing to do is just to get rid of the land as much as you can. There's a lot of different ways to do this. You could go to Sentinel-2 and do a derived water mask that way. This is kind of the dumb, simple approach that I'm doing here, which I like because it is pretty broadly applicable, especially if your area of interest is mostly water. So what I'm doing here is I'm basically binning all of the heights. And because this the area of interest is mostly water, we would expect the water surface heights to kind of pop out in that histogram. So we can use this to identify the water surface. And then you'll note here, I've just kind of set like a 1 meter buffer to avoid, capping out the water surface if there's a lot of waves. And in this case, there actually are. So you'll see I might need a 2 meter buffer for this example. So then this is actually removing those photons and setting up a new data frame with just the signal photons and the water surface and below photons. So like I said, there's a lot of different ways of looking at bathymetry in the literature. I prefer a histogram-based approach because it's a little bit simpler to explain in contexts like this. So what we're going to do is we're going to take the photon data. We have it, plotted in a long track versus height. So they're both meters, and we can bin the photon data in a histogram, a 2D histogram, kind of pixelated a little bit in a way that makes it easier to analyze and understand a lot of the time. So what we'll do here is we'll set up the resolution for that process to maybe 0.1 meters in the vertical resolution and 20 meters along track. That may seem a little small if you're used to looking at a lot of photon data, but we'll smooth out the data later to make it easier to look at. So in this cell, I'm basically setting up the parameters of that histogramming process. And then here at the bottom, you'll notice that I'm using a filter. Basically, histogramming photon data, it's points. Every now and then you'll get a lot of like empty pixels, basically. I am using the phrase pixels in probably a way that a lot of people in this room might object to, but such is life for this process. And so we're using a Gaussian filter to smooth out the data, and we'll see what that looks like in the following cell. So we can compare the photon rate if we were to just plot the photon straight out of YAPC and using YAPC to threshold it, and straight out of slide rule, we can see that in the top cell. And then in the bottom cell, we'll see what you can see this kind of like blurry image of what those photons look like in a way that's a little bit easier to analyze. So I like to look at these in kind of slices along track. So you can maybe take different points, say like 500 meters along track, 10,000 meters along track, and just kind of look at vertical slices of the elevation profile. Often you'll see kind of the water surface stick out most clearly. In very, very shallow cases without waves, the strongest return might actually be the bathymetric signal. That's really not uncommon for very shallow reefs. But it's a straightforward way of thinking about the data, and you can kind of devise basic algorithms to just kind of run along track. It's not the most computationally efficient, but it can be easier to understand. So here we'll try to, this is kind of some setup pre-configured code to plot this example, but you can manually change it if you'd like. So here I'm setting up different points along track to kind of sample the photon data at. So you can see here that 3 of these waveforms are empty because we're looking at 10, 19, and 29,000 meters along track, and great, that corresponds to where the land used to be. So we might want to manually change this as well. So we can uncomment this line here where it says inspect along track locations. And maybe let's take a closer look at this section over here, which is what we might care a little bit more about. So let's say 52 kilometers along track, 58, and what does that look like? Maybe 64. Just see if this cleans this up a little bit. Great. So many of you have probably already figured out what we're looking at, but here, if you haven't already, so we have elevation plotted in the y-axis, and then in the x-axis, you have the overall photons returned in that kind of pre-processed data. So you can see here that the water surface sticks out rather strongly, just a little bit above 0 meters orthometric heights. And you can actually see the different types of bathymetric returns. So here you have a little bit of bump around 15 meters depth. Here the returns are a lot shallower and they're a little bit more diffuse. And then here you have really, really bright and presumably a flatter seafloor as well. So you're getting stronger returns in this location along track. You'll also notice how quickly the signal drops off as it attenuates through the water column. This is actually a pretty clear case here, of pretty clear water. That's really not the case everywhere. It's a lot more common to have turbid water due to sediment, phytoplankton. Anything in the water really can attenuate the light from the laser pretty quickly. So if you're looking at a place that you might expect bathymetry and you're like, hey, this is 2 meters deep, but it's an outlet of a river and there's a whole bunch of sediment, don't be entirely surprised if you don't get bathymetry from ICESat-2. So in this next section is kind of where this diverges from a more general processing approach for photon data and more into the actual bathymetric corrections. So as I mentioned earlier, you have to account for the laser refraction through the water. There's been a publication from, I believe, Christopher Parrish and Laurie Magruder that addressed this in 2019 that provides the basic geometric corrections to do this. I've provided a function here that I just kind of transcribed from that paper here. As in the previous tutorial, this may be something that you would want to kind of throw behind the curtain and maybe just call as needed, but it's here just so you can take a look and see what's happening under the hood. You can see the various geometric corrections. This function is the key reason that we used slide rule extra processing parameters to pull out reference azimuth and elevation. Those are kind of critical for this as well. You can technically do the correction without those, but depending on if the satellite is in the middle of a high up pointing maneuver, that the difference in that correction is going to change, perhaps significantly for your use case, perhaps not if you're looking at a more general, lower confidence needed area of interest. And then just to scoot back up really quick. So here I've defined kind of a basic approach to processing these waveforms that I showed above. So you'll notice here, just to remind you, you have the water surface, and then you have a peak beneath that corresponds to bathymetry. So we use SciPy. SciPy has a built-in function called find peaks. That's pretty good for a lot of basic stuff like this, where you can just kind of, you give it the waveform, you can set a threshold for what heights you actually want to consider a valid peak. Particularly, we'll also use prominence. So that's basically the height of the peak above the base. So it's a little bit different than height, particularly in bathymetry. If you have turbid water, you may have a really strong bathymetric return, but it's a really low prominence return. So we'll use prominence here. I found it to be really useful in my own research as opposed to height for bathymetric extraction. So here we're just using the topmost return as the water surface. As I said before, sometimes in really shallow cases, the bathymetric return can be the strongest. So I would recommend using the top return instead of the strongest return, even though that might be what you might do first. We're considering all other peaks to be possible bathymetry. And then we're sorting by peak height and prominence to extract the most prominent subsurface peak, and that's going to be our estimate of bathymetry. So this isn't groundbreaking research, this function. I have no problem. You can take it and modify it. The point is that it should be straightforward to understand and to modify for your area of interest. You're probably going to see in this example and maybe any other examples that even some of the ones that I've pre-selected, there's going to be a lot of bathymetry left over, or there may be some bathymetry missing in really deep waters. If you have really turbid water, you may get some false bathymetry extracted using this method right underneath the water surface, but you can filter that as needed for your area and for your intended use. So you'll note that this refraction correction does also return planimetric corrections, so not just depth, but also in terms of easting and northing. We actually don't use those here because they're generally within the scope of the laser footprint, so it's not particularly meaningful, and I wouldn't really recommend spending a whole lot of time trying to make sure that everything is correct with respect to those corrections, but the depth correction we do absolutely need. So this cell seems like there might be a lot going on. Don't stress. It's basically just the cell that runs along that pre-processed data, and at each location along track, it applies the function from before to try and extract the bathymetric peak and the water surface return. So you'll see that here. We're kind of set up in a for loop, just running along track in the data. We select one of the waveforms from wherever we are along track. Just like I said, we run this function. So you'll notice here that we can pre-configure the minimum height and prominence requirements. If you're having trouble with the data that you're looking at, I'd highly recommend experimenting with these two in particular and seeing if maybe you want to set a higher threshold or a lower threshold and then apply extra filtering afterwards. We'll use the function, we'll use what that function returns to extract the actual elevations from the water surface. And then here we get all of the photons from the subsurface data. We isolate the photon heights and the azimuth and elevation, the reference azimuth and reference elevation for those photons precisely. And then we compute the refraction correction, so DZ pH. So for any of the photons in this bin underneath the water surface, this is the correction that you would apply to the photon heights. Although you'll remember that we also binned a lot of this data along track, so we probably have some segments that we want to look at. So we can similarly apply the refraction correction at those segment rate, and that's what we're doing in the next section as well. And then if you remember at the start, we said, hey, a lot of the bathymetry we're not really expecting in this area to be underneath 0.5 meter, and that's more likely to be noise than anything. Or we're not really expecting bathymetry to be more than like 25 meters or 40 meters, depending on your area. So then this function just kind of removes, this snippet of code just removes those photons from consideration as well. So then lastly here, we'll plot, should have run the cell a little more. Great. So here, you can see the original photon data in gray in the background. So that's the uncorrected data, and it's also including land returns as well. In black, you can see what we've considered signal in terms of the water surface and YAPC density, using those to filter. So the photons that are signal are in black. In blue, we've plotted the water surface that our function extracted. And in red, we've plotted the bathymetric returns that our function extracted. So I was thinking of last night about some ways to improve this, and I was going to try and switch this into some interactive plots using HoloView plot and various other things. But so for now, if you want to take a closer look, you're going to have to manually change the reference, the plot limits here, like I'm about to. So let's maybe take a closer look at this section in the furthest part along track. So we'll zoom in a little bit at 50 kilometers and 65 kilometers along track. So this is a little bit clearer to see what's going on. This is also, I love this track because you can see such a difference in the waves depending on how much bathymetry you have underneath the water. Even here where you don't have bathymetry, it's a little bit deeper. You can see the wave action picks up a little bit. But for our purposes, you'll also note here that maybe you have some bathymetry that's erroneously picked up here, like in the water surface. Like I said, this isn't the be-all end-all approach to bathymetry. It's kind of just to get you rolling if you're interested in taking a closer look. Yeah, Tyler? I'm not a notebook wizard, so it's been a minute since I've looked at all the magic commands. Thank you, Tyler. Oh, amazing. Okay, so now I can zoom in here and show you what I was talking about. So you might have some errors, particularly if you have like really wavy areas. The method I provided here is maybe going to be a little bit too simple. So just something to note before you take this and start sharing with all your friends on boats and saying, hey, you know, it's really shallow, and they're going to be like, what are you talking about? So you can also see the difference in here between the refraction corrected data and the original photon data. It's a little bit weird because it's like overplotted over each other, but that's just to make it simple in one plot. So you can see why this correction is important because it is a non-trivial height correction, even in shallow water. It's about, I think, 70 to 80% of the heights should be different. So that is an absolutely necessary step. And then lastly, you'll also note that this doesn't get maybe the deepest bathymetry. So the reason for that, as you might have already seen in this example or yours, is that density changes a lot depending on where you are in the water column. So you may have a really dense photon cloud 1 meter beneath the surface because you have a bunch of sediment there. But you can still see bathymetry 20 meters underneath the surface that's maybe 10% of the overall background rate higher up in the water column. So that's definitely something to be aware of and to calibrate your approach a little bit more carefully for. So for this example, because we used basically just one threshold, no matter where we were in the water column, we might miss some bathymetry here in order to remove a lot of the fake noise returns elsewhere where there's not actually bathymetry. So I see I'm coming up with a couple minutes left. So this is just the last plot is to inspect. So we'll quickly kind of sort our data frame, and we can first of all add a column for depth. So we've provided water surface heights and bathymetric corrected heights, so it's pretty easy to just get depth straight from that. We've also removed any points in the data or any points in the along track where we think that there's really no bathymetry data whatsoever. This is just for plotting purposes here. And then the next cell should plot our area of interest, and it should overlay the depths that we've extracted in a way that should be interactive and should look very, very nice. So you can see here for this reef, you can actually see pretty clearly just in the ICESat-2 data, and also your intuition looking at the satellite base map, you can just see how it's shallower, closer to the edges of this atoll, and then you can just watch it get deeper, and you can even see that the ICESat-2 data corresponds fairly well with this bed form down here. It's pretty amazing to look at. I could spend a lot of time just plotting this and looking at different areas. The other thing to note here is that you may say, okay, well, great, how do I save this and do other things with it? The way that this notebook is formulated organizes all of this bathymetric data into a GeoPandas data frame. So from there, you can use any of the built-in functions for writing to files in whatever format you'd like. So I provided a couple helpful links here. There's a little bit more information about current bathymetric research from the ICESat-2 Bathymetry Working Group, which I'm a part of, and some of the just kind of background information that you might need if you're interested in taking a closer look. And then I've also provided a link to a Python package developed by Nathan Thomas out at NASA Goddard, where he's done a little bit more careful handling of some of the things that we've talked about today. So if you say, hey, I don't really want to become a bathymetric photon extraction expert, you might look at that. But this is a good baseline for understanding what he's doing as well. So that's it for this talk. I'm happy to take any questions. And if you have any questions, or for me personally, and you want to get in touch, my contact info and email are there at the bottom of the notebook. Thank you all for your time.
Yeah, so given the green wavelength that we have with ICESat-2, how deep do you think we can kind of like confidently do bathymetry with ICESat-2? Is there kind of a range you have in mind, or is this just dependent on the water column, like you said?
So there's the theoretical max limit, and then there's the practical max limit. And I'll speak to the practical max limit, which is the deepest I've seen. I think is like 80 meters unrefracted. And that took a lot of work to find. I'm going to be honest. I was looking at reference bathymetry maps and like water clarity maps, and that was in Anguilla in the Caribbean. So it's pretty promising. In fact, there's actually been some work recently showing where the ICESat-2 telemetry window over open water is actually a little too shallow. So we've looked at places where we might have really clear waters and good bathymetric returns from reefs that we might be expecting to see photon data there, but the way that the satellite processes photon data on board, it will trim a lot of that data away for good reason, because you get a lot of data over the oceans and like you don't want to save all of it. So there's been some work going on from some folks that I work with at UT Austin and a lot of folks out at NASA as well to adjust that telemetry window to get deeper returns in places that we might not be getting it before. So I make that note because I think that we might actually start seeing a lot deeper bathymetry in places that we might not have been seeing bathymetry before as well. So pretty deep so far, but we'll see what happens in the next year or so. Thanks.
Somebody else has a question. So you mentioned this, and a few other people have mentioned YAPC. What is YAPC, and what is your intuition for how to interpret the output that you are getting, other than, I assume higher is better?
So that is a great question. So as far as I know, and I will defer to anyone who has more experience in this because I have a very limited experience of YAPC, and I'm using it here primarily for demonstration purposes. Haven't used it extensively in my own research, but it is a density-based measure of signal confidence developed by, I believe, Jeff Lee out at Goddard. Does anyone have more insight into how you might want to set those parameters?
So with release 6 data, if you're looking at ATL03, there's a built-in YAPC as weight_pH. So right now that's sort of the best. And then what YAPC is that it uses, you're right, clustering to figure out how close photons are within a certain window. And so the closer the photons are, the more likely we think that they are signal. I would stick with whatever the defaults are first within slide rule, and then adjust from there if you're finding that you're not getting exactly what you want. Susan Howard, who works for ICE with Lori Padman to try and piece out icebergs, did a lot of work. And Jeff Lee is also still tweaking his algorithm for release 7. But for right now, if you're using slide rule and trying to get YAPC, I would stick with the default as like just a best case, because that we're using what Jeff Lee used for release 6. And so that's how I would stick it. Beyond that, it's kind of just experimental, and you might be able to tweak out and get better scores. But I don't have a recommendation on something better.
Yeah, I would just say the name of YAPC is yet another photon classifier. So that's Jeff's kind of joke of, there's no best way to classify photons. He thought, let's do this density-based approach to get something in a different way. And I think what we found is that, like, the algorithm, like Tyler said, can be tweaked, especially and be, look more useful over different surfaces. And so Jeff is really open to, if you're like, hey, if you just did this, like it might pop out more in YAPC, and then we could include those in the product. So if you, really like YAPC and you really want to engage Jeff and, could you tease out something more, it could ultimately improve the product. So yeah, I would suggest just be in touch with Jeff.
Sounds good. Thank you.
Yeah, thanks for this. This was really interesting. My question, so there was this thing like in the early days of like ICESat-2 where people were like, worried about specular returns when doing shallow water bathymetry. So you would like get like these additional returns just under the water surface, usually like 10 centimeters or so beneath. So my question is that a thing that you have to worry about with your histogram approach, or is it even really a thing that's a bother anymore?
I think it's like you definitely account for all of those. It comes down to kind of different use cases. For one, is the first thing I think of. So people looking at depths of coral reefs just to kind of get a measure of vulnerability to warm waters may have different standards for quality in their bathymetric extraction versus people looking at charting for NOAA or the hydrographic services elsewhere. So I think most people looking at ICESat-2 tend to apply kind of a base level threshold of maybe only looking at things at deeper than 1 meter, just because it's easier to kind of remove effects from things like waves, which tend to be a bit more driving in terms of errors, especially with a histogramming approach. If you're looking at density-based measures, depending on how you've configured the density filter, that may also be easier to sort out. But I think most people just kind of tend to focus on bathymetry and then maybe the 2 meters and deeper range, just because it's easier to say with high confidence what you're looking at.
Quality flags for possible afterpulse effects.
Yeah. Yeah, and it's so open altimetry will show you as well. Like it won't show the flag necessarily, but if you pull up maybe some photon data over the Florida Keys, you'll probably find maybe one in every view that you're looking at is going to have very, very strong returns between 2 and 4 meters underneath the surface that are going to look very, very unnatural. And you're going to say, what is that? And that's what you're looking at. So quality pH on the ATL03 data product is a great way to filter for those if you expect that that's going to be a problem.
Okay, thanks a lot, Jonathan.
Thank you.